Right, it's going.
All right, well, okay, maybe we should wait for more people to join. So I don't know how many people were attending last time.
I think we are only missing Ambrush, and let me check. Which one is? Okay, it's this one. Oh, it doesn't show anymore who was there. We are missing Balint Köműves. He was commenting on the previous week's chat, and there was someone called Bence Ország, and I think, oh, it's showing, right? Yeah, I think that's the two of them who are missing both as guests.
Köműves Balázs is here.
Yes.
Okay. Sorry, it's just checking the last week.
But maybe I should just start. Okay, so this is the third session of this meta theory of type theory seminar. And well, last time András defined so there was the full definition of categories with families.
Well, you know what I'm going to say, right? You know my first comment in every one of these.
I'm not sure.
To increase the font size.
Is this good?
Yep, thanks.
Okay. Okay, so we have seen the definition of so categories with families. So that's our notion of model of type theory. But I think we have not seen any types or term outside of the basic structure of categories with families. So I think we'll now see how to define some. Okay, and in the first session we had defined so we had defined some simple language with some types like Boolean and natural numbers, like this. So now we should define as well some types and terms for dependent type theory. Okay. So maybe I should start with, okay, let's start with Booleans. Okay, and so we'll recall the main components of categories and families. So we have contexts, substitutions, types in a given context, and terms of a given type in some context gamma.
Actually, I have a question about this.
Yes.
So if we only take contexts and substitutions, they are the category, right? So it's category
Yes.
with families because the first two are the category and the rest is the extra stuff.
Yes.
So I guess my question is, so when you say that con is a set and sub goes from con to set, so if we just restrict ourselves to a category, we would say that con are the objects and sub are the arrows or the morphisms.
Yes.
So but in this formulation, we don't really have to say where objects and arrows are, right? We don't necessarily have a background substrate in which objects and arrows live. We just say that, oh, we have objects and we have morphisms between them. So I guess, right?
I'm not sure. We still have a set of objects and a set of morphisms. And then maybe we can change set with something else.
Yeah, but my question, yeah, exactly. So my question is not if we should change those. My question is that usually we allow those to be anything, not necessarily set, and we don't even say what it is.
What do you mean by anything?
So well, like larger.
Usually the objects can be any set. So.
But it doesn't have to be a set, right?
Or usually it does.
I think there is like
so there's a
misunderstanding.
So there is the category of sets, and in that category, the objects, we have a set of objects, and this is the set of sets. Well, there are some size issues, but that's it. But then there are other categories in which the objects, the set of objects is not the set of sets.
Right, but the reason, so the reason that I bring this up is because when we say that type or tie is then goes to set and term goes to set, I'm just not sure what those sets mean if I try to interpret them the same way as when we say that con and sub go to set. Like for con and sub, yeah, okay, so they're going to be objects and morphisms, but when tie goes to set, like I'm just not sure if this is.
So this says that in every context we have a set of types.
But I mean, but can't you define the notion of a category without even knowing about sets?
And you can use another symbol here instead of sets. I mean, no, not really, I would say. I mean, you need to have some meta theory, and if you have some different meta theory, maybe there's some different definition of category. Maybe but.
I mean, the only reason I'm bringing this up, so this is not to nitpick. I'm bringing this up just because if we are talking about models of type theory, then I imagine the whole point is that we want them to be very different. So they might not even, like, how should I put it? Like, if we're talking about models of type theory, doesn't that mean that there should, yep.
So I guess you mean that there should be some more general notion of model in which contexts are not sets. In which we don't have a set of contexts, we have something else. Is that what you mean? I don't really.
Yeah, but when we just say that, oh, it's a category, and then we want to add these extra things without tying, without necessarily restricting ourselves any further. Like if we were talking about models of category theory, right? We wouldn't start with saying that the objects form a set and the morphisms between.
No, but that's somehow that's not on the same level. So when we study categories, we say that objects form a set and morphisms between two objects form a set. But then if we move one level higher and study models of category theory and not of categories, then we may do something like that. But here we just want to study models of type theories and not something at some higher level.
Okay.
I'm not sure if.
I have to think about it, but okay. I don't want to.
This notion of model is. And so yeah, we could generalize, but this is somehow universal and good enough for almost everything.
So I think the only difference from the usual definition of category in classical mathematics is that this is called small category because so it's only cardinality different.
Well, okay, but then we can index with different universe levels.
Yeah, but
I just don't want to talk about
it, not for you. So I think this is the classical definition of category.
Yes.
Just for example, the set of all sets doesn't exist. So the category of sets doesn't fit into this, but it's only like a cardinality type of. The set of sets is too big to be a set, but that's the only difference from the usual definition of category.
So Balázs, just so that I understand, you're right. You're saying that if you start from scratch and you want to do category theory, so nothing about categories with families, just normal category theory, you will need sets before you can do that. Like you need, I don't know, ZF or something before you can do category theory.
Well, you need some meta theory. Okay. So.
I mean, no, I don't know how to answer what you asked, but. But this is the definition of category. Just the only problem is that the set of all sets, you cannot. The category of sets, for example, is not fits into this definition. But the only reason for that is Russell's paradox. So I mean, if you are okay with like small categories, we are in computer science, so everything is small in mathematical sense. Then this is completely fine.
And that's not true because we will later define large categories with families. Okay, but
we can just treat the like a size of sets as a kind of technical detail. It's not very essential.
I mean my question is not so much about the sizes; it's more about whether we need set theory to be able to talk about this. Because at one point we wanted to use type theory as a fundamental.
And this can be this could be in type theory. This could be a type if you want. It doesn't matter. We work in some meta theory. It can be set theory or type theory.
But it has to be a set in the sense of homotopy type theory.
Yes.
Even if you are working in type theory.
You mean it has to be an H set if it's a type? Okay.
Yeah.
And because it has to be a one category and not an infinity category. But
actually, why would an infinity category be a problem? I mean, I think of these things as in geometrical sense, then it's not necessarily a set. Why is that the problem?
Well, anyway, I think we're somehow out of. Well, I don't know.
Okay, it's not important. Just continue.
Okay, so there was this theory structure, and we also had ID in sub gamma and composition. Sub delta and sub delta and gamma. So if you have a substitution from gamma and from theta delta, we have a substitution from theta gamma, and then there are some laws here, and then we had types and terms plus some substitution operation. So we have a type in gamma and a substitution from delta to gamma, we get a type delta. And then you have the same thing for terms. If you have a term of type A in gamma and a substitution from gamma to delta, from delta to gamma, we get a term in delta of type A substituted by sigma. Oh, by the way, if my keyboard is too loud, I can switch to my laptop keyboard. Just tell me. So we have types and terms. And then we had the empty substitution. That's a substitution and the empty context. And we had context extension and extension. So this was this operation. Context. Extend the context with a variable of some type, with a new variable of some type. And on substitution, we extend the substitution from delta to gamma. With a new term. Okay, so if you have gamma and A as above, we can extend a substitution. So a substitution is like a list of terms in the context gamma, where the types are given by delta, by gamma, sorry. And now if we extend gamma with A, to extend this list of terms in the context delta, we need to add some term A to it. And then there were some other operations and equations related to this. But these are the main components of categories families. Okay, so now we want to add a type of booleans. Okay, so we add some type there we have two choices. Either we add a type in the empty context, like this, or we add for every context a type in this context. Okay. Along, but okay. So if we choose the second option, we have to add some laws that tells us that this type is the same everywhere. So that this says that for every substitution sigma, if we substitute this type, that should not depend on the current context, while we get the same type. So we can call this, we can give this name to this rule. Okay, so let's so two options. Either this type is defined in the empty context, but then when we use it, somehow we need to implicitly, and so we can. So here we had, yeah, we have epsilon, so we can just okay. So if we want to bring this type to another context that is not the empty context, we can use the substitution epsilon to bring it to any context. And otherwise, you can have already we can already say that it's available in every context, but then we have to add this equation that tells us it's the same in every context. Okay, so we have this type of Boolean. It should have two values, true and false, or yeah, PT and FF. So let's pick this second option. So now we say that true and false are terms of type bool in any context, and we also need to add some substitution laws that tells us that when we substitute true with anything, we still have the same thing, and the same thing for false. Okay, there's some discussion in the chat. And the final thing to define Booleans is some if then else construct. Okay, and we can use the same, more or less the same definition as the first session. So in any context gamma, if we have a type in this context, no, a type, but additionally depends on a Boolean value. Then some case for the true branch of the if then else. And a case for the false branch. And if you also have a Boolean, then we should get some value in gamma of type A substituted by B. Well, okay, so this is the eliminator for the type of Booleans. So it tells us that to inhabit a type that depends on a Boolean value, well, we just need to provide the cases for the cases when this Boolean value is true or false. And maybe before this, we also have a simpler non-return in eliminator, where A is just a type in gamma, and false are just some cases, and B is some Boolean in gamma. But this non-dependent eliminator is not sufficient to characterize Booleans when studying dependent type theory. So we need to use this dependent eliminator. And then, as in the simply typed case that we have seen in the first session, we need to add some equations. Namely, if then else of A TF true is T, and if then else evaluated.false is this value F. And as in the definition of these previous types and terms, we need to add some substitution rule. So let's write all the types in detail. So we have first A. Yes, we have these types and terms. And we also have some substitution sigma from some complex delta into gamma. And we want to say that when we substitute if and else with sigma, we can move a substitution sigma inside to A, T, F, and X. This was B. And okay, so for and there we need to substitute A, T, F, and B to bring them to the context delta. And for the last parameters, this is easy. But for the first one, for this A, well, we don't have yet a substitution from anything to gamma extended with B, because we just have this sigma, and that's a substitution from delta to gamma. Okay, and so we introduce some operation on substitutions. So we say that we have sigma plus, and that's a substitution from delta extended with bool into gamma extended with bool. And I will define it with the combinators that we have seen that have been introduced last time. Next, but if we have this, we can substitute A and obtain this this substitution rule for if and else. Okay, so how is this substitution defined? So the idea is just that so a substitution is a list of terms of type with the types in gamma and a Boolean in this context. And on gamma, it should just be sigma, except that we need to, because sigma is in this context delta, we need to move it to this larger context. And this Boolean will just be the Boolean that is the second value here. Maybe I can find a way to write it with variables. So if we write this context with variables, it will be something like this. And if you write the second context, with variables, you get something like this. And the substitution sigma plus should be it should give a value for gamma and a value for b. That depends on this context. And for gamma, it should be sigma at delta, and for b, it should be b. Okay, so this is this is some notation using variable names, but this can be translated into the combinators by saying that sigma plus is some extended substitution where the first component is sigma composed with p, where this p was the substitution from okay, so this was
P goes into delta, right?
Right?
Sorry? P goes into delta.
Yeah. So this P was one of the operations of CWF. So whenever we have some extended substitution, we had some substitution back into it, back into the base context. And it also came with an operation Q that was term delta extended with B with bool of type bool. Okay, so in general, for when we have this was defined for any type A, and there we have to substitute A with the B that is above. And because we have the substitution rule for Booleans, for the type of Booleans, there we can just forget about the P and just have Booleans. So this Q is just the variable of type bool in this extended context. So P and Q are the first and second projections that that get delta and B from this context. Okay, so here we get, so we say that the first component of this sigma plus was this gamma component here, and we say that it is sigma at P, so that's the component, sigma composed with P, so this P was the component delta here, and then this composition with sigma was this application of sigma. And then the second component is Q. So that's yeah, the same as this. Okay, so in other words, we have some operations that can be derived from the basic operations of a CWF, and that the operations of a category with families, and we use these derived operations when defining this kind of substitution rules. Okay, so this is the full definition of the types of Booleans. And I think maybe it would make sense now to instead of going through all of the standard type formers of type theory, to look at the standard model, and then we can see what the standard model has and how we can reflect it in the syntax. So is this definition of the structure of Booleans on a CWF clear for everyone?
Maybe we could look at some examples involving Booleans, like example terms involving.
Yeah. Let's see. For instance, we can define not. So what is not? So not. So we don't yet have any types for functions in our language, but we can say that not is an expression is a term in a context that has a Boolean. So not. Okay, but I think I will try to use. It would be good to have a way to use variable names for contexts. I mean, I will just use variable names for contexts. Okay, so yeah, whenever I use variable names, it's a way to refer to some composition of P and Qs of the actual context. So the variable name B is not part of the context. It's not part of the real context, but it's just notation to make things simpler. Okay, so not should be a term of type bool in a context with variable B. And so it will be if then else. Well, at the end, we apply if then else to the Boolean B. And the type that we want to return is just the type of Booleans. But when B is true, we return false, and when B is false, we return true. Okay, so is there anything else we can define so far? I think we can only.
We could maybe.
I get.
We could maybe look at the dependent eliminator that the substitution rule that the types check out, because I don't see immediately how the types check out there, because it's a bit complicated dependency involved in here.
Okay, so we can check this. Okay, so
Sorry, just a question. So the not should be not be equals, right? Because that's a dependent variable.
Yeah. So.
No, at the equals sign. So should we write it as not be?
Well, I mean, it's mainly syntax, but so if we didn't have if here I just had written this context without using variable names, then we would not write b. But if I do this, then I can maybe write this so that we remember that this is the same context here and here.
Can you give the same term in the Debrenne style?
Yes.
Thank you.
So that's with variable names. And with the Debrenne indices, so this would be this context, and here we need to refer to the first variable of the context. So that's
just Q.
And yeah, that's just Q. But if he and we can also use the if I can type it. Yeah, we can also use this notation. So we can say that this is the first variable of in the context. So that's 0 as a Debrenne index. And if we, I guess we can define end. In both styles as well. And AB, it will be if then else. So let's use A as our Boolean here, and we still return Boolean, and if A is true, then return B, else return false. And you can also write it with Debrenne indices. Okay, but now we need to replace A and B with Debrenne indices, and this A is 1, and this B is 0. Okay, so yeah, so there was some requests about the types of this. So this is a term in the context delta of type A. So first there's this one. That's a term gamma of type A substituted by substituted by ID, B. And now if we substitute with delta with sigma like this, we just substitute this type with sigma. And on the other side, it will also be a term in the context delta. And if we compute the type using this, it will be ID, comma, B sigma. Wait, no, A sigma plus composed with ID, comma, B sigma. So to check that the types match, we need to check that the composition ID, comma, B composed with sigma is equal to this sigma plus composed with ID, comma, B sigma. Well, and actually, if we use the rules for the equations for composition, we should notice that they are both equal to it should be sigma, comma, B sigma. So we had the so just by using the equations that are in the definition of a CWF. But if we write the same thing with with variable names, then we don't really have to do this computation because it becomes somehow it should become obvious just because we don't have to do, because in this notation there's some hidden shifting of the Brun indices that doesn't happen with variable names. Of course, then we have to prove that that doing the computation with variable names is and also proves the fact that the computation with the Brun indices is correct.
I mean, if you are using names, then this example is perhaps obvious, but in general, it's not unambiguous. It's possible to make the incorrect computation if you are using names.
And if you are using names formally, and if you're only using names, yes. But I guess mainly because you can have collisions between names, and it should be forbidden.
Yes, but it's also possible to have some implicit weakening, which is not obvious because you have multiple.
That's true, yes. There we can try to compute with this, and we can see that and substituted, for instance, with true, it will compute true. And in fact, for any B and true B, we compute to B. However, if we swap the arguments and write B proof, this will not compute to, because this will compute to if then else B true false B, but we don't have any computational rule that tells us that this is equal to B, even though this should be the case. In our understanding of even else, but in the syntax, it's not true, and yeah, this means that there are models in which this is not true. Yeah, so I think we should define the standard model and then define some additional structures, both in the syntax and in the standard model. So what is the standard model? So far we have only we have seen that there is an initial model. That's the syntax. I think we also have seen the terminal or trivial model, but it's not very interesting. And now we want to give semantics to our language. So the idea of the standard model, the idea is that if we manage to prove some things internally to our language, we also want to prove that it holds in our meta theory. Let's call the initial model I, and let's call the standard model S. And well, essentially, this standard model will not be very complicated because, well, for instance, the booleans will just be interpreted by the set of booleans, and everything will be interpreted by things that we already that we are already familiar with in the meta theory.
So does that mean that the term of type A will be modeled by values of type A?
Yes, well, a type will be a set, will be modeled by a set, and terms will be modeled by elements of that set.
Yeah, sure, but wait, but that's not what I meant. What I meant is that we have more terms of type bool than just 2. So if you say
in the
that,
syntax, yes.
Yeah, exactly. So that means we need to the standard model to do some real work to figure out which of the 2 values each term will be represented as, right?
Yes, so indeed the interpretation from the syntax to a standard model is going to compute something.
And also, a type is, so only a closed type is a set, and the closed term is an element. So if you have open types and open terms, then they are functions going from the interpretation of the context.
Okay, so first we need to define the CWF part of the standard model. And so what are contexts? Contexts are sets. And we maybe let's look at an example of okay, so if we look at the context with two booleans, it will be the set of pairs of booleans in the standard model. Then substitutions from delta to gamma, plus functions from delta to gamma. And the types in gamma, maybe I can do the empty context first. Okay, so the empty context is the set with only one element. So in particular, there's exactly one substitution, one function from any set into that set. Now a type in gamma is a set that depends on gamma, so that's a function from gamma to, I mean, that's a set that depends on the set gamma. And terms of type A are elements of that set for every gamma and gamma. Okay, we just need to check that we can extend context. But if you want to extend a context gamma with a type A in S, this should be a set, and it will be the set of pairs with gamma in gamma and A in A of gamma. So, and we can check that if we have, maybe let's look at booleans, and booleans would just be a set of booleans. Maybe we can do this. And we can check that this context, this is just bool extended with bool, and this will compute.
Also, yeah, empty context as well.
Sorry?
So, I mean, we have two bools, but also the empty context.
Yes. Okay. So it will be the type of okay, so if we compute using this, it will have something in this, but it can only be this element, along with some Boolean and some other Boolean. So well, that's isomorphic to this. Maybe this should be cool. Okay. And maybe we had the combinators P and Q in the syntax, and they were called first and second projection. And in this model, they indeed are exactly first and second projection out of this set of pairs. So,
I have a question. So in the standard model for terms, you have something that looks like a dependent function type, but it's
the standard model for theorems?
For terms.
Oh, terms, okay.
On line 116, right? You have something on the right-hand side which syntactically looks like a dependently typed function.
Yes.
Like, okay, have we established that such a thing exists? Are these well defined? Like, if we are
so that's
like, I don't
yeah,
know.
we assume that we have this in our meta theory.
In set, you have dependent functions.
Yes.
You do? Okay, so you're saying that like enormous set theoretic, functions which are just. I mean, I thought that the functions were just like a special case of binary relations if we are in the world of sets.
Yeah, but then you can use a different encoding of a different set theory encoding of dependent functions. It will be like a relation between I guess first you define this, the set of dependent pairs, and then you give a relation between gamma and this set. That's and you give a function from this to this. But that's just the encoding in set theory. But yeah, this should be some subsets of relations between gamma and the set of gamma A such that gamma is in gamma and A is in A of gamma.
Okay, so basically the capital, so like capital A is just like some collection of sets indexed by gamma.
By gamma, yes.
Yeah, okay. I just want to keep things clear because I'm hoping that we end up with something that's not too circular.
Some circularity cannot be avoided, I think.
That's why we have the meta-circular interpreter as a name for these kind of models.
Yeah. And okay. Yes, I was saying that the first and second projections P and Q now are just the first and second projections out of this. And to finish the definition of Booleans in the standard model, well, true is interpreted by true, false is interpreted by false. And if and else is interpreted by if and else.
Or maybe it's a bit more precise if we interpret them as constant true and constant false.
Yeah. And this should be, yeah. So yeah, because we depend on this context. So if and else will be for every value, for every possible value of the context, if and else of the terms that we have evaluated at this context. And this was also yeah, this was also constant.
But is the meta-theoretic if then else also dependent?
Yes.
But then shouldn't we use the A as well? In the
yeah, it's somehow implicit in this even else.
Okay.
So somehow, if the meta theory is very close to the syntax, then it will be translated by exactly the same kind of if and else.
Sorry, what are the lowercase gammas in the there? Yes.
There. So if you look at the definition of terms, so this should be in s.tm of gamma a at id comma b. So this was the definition of even else. And now if we compute this should be a function from gamma, from small gamma in gamma to a of id comma b.
Also gamma
evaluated of gamma.
So lowercase gamma is basically just a concrete variable from the context.
Yes.
You can think about the small gamma as the environment values. If you want to view this as some interpretation.
Yes.
So when we are writing an interpreter, we always need some environment for all the variables. And there's also a small big gamma on the that line.
Yeah. Okay. I mean, so that's the standard model. So, okay, I think maybe next we should look at the empty type in the syntax and in the standard model.
I think we left out some constructors in from the syntax in this model. For example, substitutions. Yeah. I think
substitutions. Yes. Yeah. We should at least look at substitutions. So if we have that substitution will be composition. Like this, because so here so A is a function from gamma to set, and sigma is a function from delta to gamma. So we can just compose them to get a function from delta to set. So this is the definition of substitution for types. And for terms, we still have A and sigma as above, and we also have some small a. That's a dependent function from gamma to A. And the substitution of A by sigma should be a dependent function from delta to A composed with sigma. And this is still just a composition of a function with a dependent function. Yeah, and I skipped some. I skipped, for instance, the identity. Sorry, the identity substitution from gamma to gamma, but that's just the identity function. So I don't think I think I didn't skip anything else that is important.
Substitution extension.
Yeah, that's the inverse of and so we want to extend a substitution. That's just pairing. So when we extend a substitution, we take a substitution and a term, and we want an extended substitution. That's not this. Okay.
Oh, but I have it. The small one. Yeah.
Okay. So here, sigma is a substitution from delta to gamma, and A is a term in the context delta. And now we want a substitution from delta into gamma extended with A. And this should probably be some delta. Let's look at the types. Yes, we have sigma substitution from delta into gamma, and small a term of type A in delta. And so this substitution extension should give a substitution from delta into this type, into this set. And it can be defined like this by just pairing sets. But so this means that this one was also
I don't think so. With P, you only have a single lambda in the definition, or just one abstraction, because P is already a substitution.
yes.
Maybe it's a bit more uniform if you also write lambda in P and Q, because you've been writing lambdas in other terms and substitutions.
So let's look at the empty type. And so in the syntax, we just have the empty type, a type at every context. We don't have any way to produce value of the empty type. And you have an eliminator. So we have a type that's dependent on the empty type. And a value of the empty type, a term of the empty type. We get an element of the type A.
And maybe it would be simpler without the type dependency. I think usually we don't write the type dependency because it's a kind of...
Because we don't need it, yes. Okay, so if we have any type, if we have any inhabitant of the empty type, then we get an inhabitant of any other type. Okay, so and in the standard model, it's the empty set. And ex falso, well, here we just we can just define this because we know that we cannot have any value. This and this A. Wait, no, because we need to bind gamma, and then here A of gamma is in the empty is an element of the empty set. So we can we can just use the meta theoretic ex falso to construct anything. Okay. So why is this interesting? That's because we can now use the standard model to prove that there is no inhabitant, that there is no inhabitant of no closed inhabitant of the empty type in the initial model. Okay, so why? That's so that's because we have F morphism from I to the standard model. No given a term in the empty context type bottom. Have f of A for the initial model. F of A, a term in the empty context of type bottom for the standard model. But we can compute that this is the type of functions from the unit set to the empty set. So this means so we have proven that this implies false.
So we are using this false here as meta-theoretic contradiction, but maybe we can just use the empty set.
So basically this works assuming that we have already proven the initiality of the initial model, right? Because otherwise we can't just say, oh, but we should have a morphism from.
So so we don't really prove the initiality of the initial model because that's by definition. So we need to prove that it exists, maybe, but we don't need to.
It's an assumption, basically. So.
But I mean, okay, but that's a big thing, right? Because we gave a model which we call the initial model, but we could have called it the foo model. So wouldn't we?
But by definition, it is the initial model. It is an initial model. So it means that for every other model, there is a unique morphism into that.
But that's what it means for it to be initial, right?
Yes.
But we gave a model which we call, well, we gave the term model and then we started calling it the initial model, right?
Okay, so well, we didn't give it, we defined it to be the initial model. So then there are two questions. So then the question is, are there other ways to construct it? So I guess it's like, so when in Agda you write something like, the data bool, where true is in bool and false is in bool. Okay, so you define the type of booleans to be the initial type with two elements.
But okay, so I'm totally lost now. I'm sorry. So we started with saying what is a model of type theory, right? Then
Yes.
we gave a particular model, which is one where terms are modeled by terms. So it's like the term model where every term is simply, it just is, right?
I think to be precise, so what happened here is that we defined what a model is, and then we just stated there exists an initial model, but we didn't elaborate on why it exists, or we didn't give any construction or any proof that there is such a model and it's initial. So we just skip this part because this part is actually very complicated, and this is just the setup of this meta theory. So
so in that case, I guess I misunderstood, because I thought that we defined the term model and said that it's the initial model, but you're saying that I misunderstand, and what we said is that supposing there is an initial model, we do this and this, and we never said that it's the term model. Right?
Yeah, I think that's right. So we just say that there is an initial model, and the initial model behaves exactly like a syntax. So every inhabitant in the initial model can be viewed as a syntactic object, but we didn't say anything about why, or the details of why this exists and why it is initial.
But okay, but then okay, is it the term model?
It can be constructed. So basically, it doesn't really matter how you construct it. So you can construct it from like sets of raw terms with some well-formless conditions, and it works. But you can also construct it in different ways, but it doesn't really matter because all initial algebras are isomorphic to each other.
Right, but I'm asking because I'd like to know what it feels like to hold it in my hands.
But you know, it is like asking why don't you whether you construct the abstract syntax trees using natural numbers, and how exactly do you encode the abstract syntax trees as natural numbers, because you can, but it's not an interesting issue, and it's the same here. You can encode the initial model in lots of different ways with abstract syntax trees quotiented or something like that, but it's a different topic.
Yeah, but okay, but when you say it's AST's quotiented, that's something I can imagine. That's something I can run my fingers.
Yeah, that's the best. That's a good intuition. Yeah.
Okay.
Yeah, you have ASTs, but you also have some equalities, so you identify some of them.
Right. So then, if we want it to be very precise, we would either need to show that, I guess, if we showed that that is a model, and then we showed that it is an initial model, then we could, if we really wanted to be precise, then we could get to line 157. But we would need to, so these are the missing steps. It's like, if you wanted to constructively show that there's an initial model, I imagine you would have to give a model and show that it's initial, right?
Right, but so, of course, but we don't want to do it in a like so it's a lot of work, but it's very inefficient if we demand that for every type theory we want to construct a syntactic model. So
well,
it's the,
I mean, I'm not saying we should do that. I'm saying we should say what the steps are that we skip, because it not, I mean, to me it's not trivial what steps we skip.
So I mentioned. Yeah, so this is the skip step. But if we want to actually do this, then the way to do it is to say that we have like a large class of inductive definitions, and all of the definitions have initial algebras. So in this case, we say something like every quotient inductive definition has an initial algebra, and we can prove that in a generic way, and then we just say that this definition of the syntax is quotient inductive.
So the reason I'm stuck on this point is because it seems like we have just gotten a very powerful tool, because what we have here is saying that if we prove two things, one is that we have an initial model, and two, that we have any single model which is consistent, then it seems we have proven consistency of the initial model. Yes. And in some sense, we have proven consistency of the formalism, not just any single model.
I mean, so in this particular case, the consistency proof, so the part defining the standard model is almost trivial, but establishing the infrastructure of these initial algebras is much more harder. But as soon as this infrastructure is established, we can just use it, and then it's very powerful. So you're right about that point.
Yeah, and I also mean, as in, if I want to generalize the technique over, like other things, like not just this particular language, because you could say, okay, well, we've just proven that it's consistent, so what do I care how exactly we did it? But I care because I'm curious how, like, if you gave me another language or another type theory with slightly different details, then the technique would still translate, right?
So the difficulty depends on like how different are the meta theory and the object theory. So if the object theory has some weird features, like for example, like the object theory can be, for example, cubical or has some interesting additional features, but the meta theory is just some plain type theory, then of course showing consistency can be a lot more complicated because somehow we have to model features which are not actually natively existing in the meta theory.
So in that case, the hard step would be giving the standard. No, actually, wait. Yeah. So in that case, are you saying that the hard part would be giving the thing that would stand in for the standard model, i.e., a model where consistency is easy to show?
Yeah.
Or are you saying that the initial proving the existence of the initial model would be harder? Which of these two?
I think in general we should just keep this initial model part because that can be done very generically, and it has always been. I mean, it has already been done in different flavors. So yeah, but for example, if you want to prove consistency of cubical type theory in extensional type theory, then you have to basically define cubical sets from the ground up in extensional type theory to make this work.
So the stand-in for the standard model is the part that would be much more complicated.
Yes, in that case, the standard model is really complicated. And the other part, you can always just think of it as part of the setup. So that's something which you have to prove once for every quotient inductive signature, and then you can just forget it and use it.
Okay, so okay, that's very interesting. So what you're saying is that as long as I can present my type theory in the same form of let's say inductive definition with extra equalities, then I can pretty much just get the initial model because the work has already been done sufficiently generically that.
Yes.
Okay. Thank. I didn't know any of that, but this is okay. This is very interesting. Thank you.
Yeah, so I think the next steps here are to define some more interesting types in both the syntax and the standard model.
Sorry, Raphael, do you want to say something about substitution laws for the empty type, say, that we also need?
Okay, well, it's the same as for Booleans. But yeah, so for every type or transformer that you introduce, you also introduce a substitution law. But in principle, it can be automatically derived. So writing them is a bit tedious. For instance, these are the substitution laws for bottom and ex falso. So we can now look at more interesting types, such as bitypes. The type of dependent functions. So let's take some context gamma, a type A in gamma and type B in gamma extended with A. And somehow in the what happens is that in the syntax, we already have a way to talk about dependent functions from A to B, because we can talk about terms in the context gamma extended by A of type B. So I guess we could say that it is the you can say that this set contains the dependent functions from A to B, but it's only a set, an external set, and not some internal type. So we cannot talk about it internally, and that's what we get by adding pi types to the theory. So we add pi AB. Here is a type in gamma, and we want the terms type pi AB to be the same as this. And what does that mean? So this means that we have some operation app for application that goes in this direction. We have an operation for lambda abstraction that goes in the other direction. And we have the beta law that says that application of a lambda, so that's actually f, so that's f in here. Okay, so applying some lambda to some lambda just gives back what we started with. There, I should say that there is another way to define application that is probably the one you would expect, with 2 arguments instead of 1. Like this. But this definition of application is equivalent to this one. And this one is called the categorical. And
it's a homework to prove the equivalence, no?
Sorry?
To proving the equivalence is a very good homework.
Yes. Okay, so and then if you go through this equivalence, this beta law will just become the usual beta law. So So applying some lambda to some argument will be the body of the lambda substituted with this A. And this isomorphism also implies that the Italo is satisfied. And it says that given any element of the pi type, well, any element of a pi type is equal to lambda. And that's it. This is the definition of pi types. And we also, well, yeah, in practice, we also need to look at we also need to define the substitution laws. So we also have a substitution law for pi, for app, and for lambdas. But I don't know if I should write them explicitly. Yeah, the only thing to note is that to deal with things in extended contexts, we should use the this operation sigma plus, as we did here for this type A that was in the context extended with a Boolean. Maybe I can. Okay, can we define some terms now that we have pi types and Booleans? Well, for instance, now we have some. And define not as a function. So it's a term in the empty context of type pi bool. And it's defined as lambda of the previous knot that was defined before. So let's write directly this. Okay, but that's not very convenient. So it will be more convenient to just say that we bind some name here, and this name just stands for the correct de Bruijn index. So we have not. Can we do it? Yeah, maybe you can define some. Yeah, I don't know what should be. Yeah, you can define a function that applies true to some. So we can define some higher order function. that takes the functions from bool to bool and returns the bool. So I think that currently we don't have any way to write proper dependent functions because we don't have any dependent things in the syntax. So we can only use functions, non-dependent functions. There was a question.
So lambda not. It's basically a transformation of the original function onto an X. So it moves the term from one context to the other by removing or adding the dependency. Do I understand it right?
Yes. So this operation lambda, it takes. So here the dependency is expressed by this extended context, and here it's expressed by a pi type, and we can move from one to the other.
Aha.
So inside the lambda, you have to write a term which binds an extra variable.
Yes.
So that's why the lambda behaves exactly the same way as the usual lambda, except that we are using De Broglie indices. So inside the lambda, you always write some term which binds an extra variable, and but the application is a bit different. So because it's not like the usual application, but the usual application can be derived from this definition of application.
So we can define this higher order function. It's lambda, then it binds some f and applies f to true. Okay, so then to define it, we need to define this usual application using this categorical application. So if you want to write it with Lebrun syntax, we just write this. And then if we take, if we write pi true applied to not prime applied to I don't know. Not prime. We can write it to app prime or not prime tt by this rule by beta prime, and then we can create this to this again by the same rule, and this is false by implication rule of if then else. We can now compute with functions internally. And in the standard model, pi types will be interpreted by the dependent functions of in sets. So be like this. So given, okay, so here we have A is the type of a standard model over gamma, so that's a map from gamma to set, and B is over gamma extended by A, so that's from this type of pairs to set, and the by type, it's a map from gamma, so it's a set indexed over gamma, and at some gamma, it will be the set of functions from A at gamma to B at gamma and A. I guess that's defining application and lambdas in the standard model can also be homework. And we can have a look at sigma types. And actually, sigma types depend on the same thing as pi types. So we have a context gamma and the type A over gamma and the type B over that depends on A. And now we look at the type. We look at this type, and this set. It's not a type. The type of the set of pairs with A, a term type A, and B, a term of type B substituted with A. And well, it's only something that is external. But we can make it internal by saying that we have this sigma type such that terms of sigma AB are the same thing, are isomorphic to this set. Okay, concretely, what does that mean in terms of operations? We have a first projection, pi 1, goes from terms in the sigma type to the first type, and then we have pi 2. It goes from terms of the sigma type to the second type, substituted by the first projection. Okay, so that's one direction. In the other direction, we have a way to construct elements of the sigma type. And then we have laws that tell us that both compositions compose to the identity. So on one side, this says that on one side you have theta laws, pi 1 of pair A, B is equal to A, and pi2 is equal to B. And we have an beta law. That's a pair of A1, P, pi2P is equal to P. Yeah, and then we have some substitution laws. For these. Yeah, so yeah, somehow the construction of pi types and sigma types is a bit similar because we have some extra thing that you can construct on terms, and we make it internal by adding some type such that terms of a type are characterized by some universal property. I guess as an example, we can look at yeah, I don't have any example in mind for sigma types.
I think returning a sigma is the simplest interesting example, because if you don't have sigma types, then we cannot return multiple things.
Yes.
To a function. Of course, we don't yet have any interesting dependent types, but we can just write a function which returns a pair.
Yeah. Okay. F is a function on booleans that returns booleans, and F is a lambda that binds a boolean and returns a pair with not the boolean and the boolean that you are given not B and B. Yeah, I don't think you can. Yeah, if we had natural numbers, we could define Fibonacci, for instance, using sigma types. But here, I don't think we can do anything interesting. We can quickly define sigma types in the standard model, because we don't need to change much from the definition of pi types, at least on the level of sigma and pi type formers. So if you have a set indexed by gamma and the dependent set over it, then the sigma type in the standard model is just given it's just given at every gamma and gamma by the type of pairs of A and B. People are leaving. Yes, I think this concludes today's session. Are there any remarks?
What should we do next time? What do you think? Should we look at more type
maybe some simple presheaf models?
Mm-hmm.
Like we could define
I think
we could prove that the law of excluded middle is not provable in the syntax.
Mm-hmm.
But for that we need a bit more type formers. So we need identity types, and
no, we just need some types.
Mm-hmm.
Oh yeah, we need universes.
Sorry, did you introduce universes, Raphael, or not yet?
No, I didn't.
Mm-hmm.
I think we should do a universe and identity type next time.
And then we